Here we are going to discuss some problems on the moment of inertia, where we will use the transfer of the mass and some theorems to calculate. As you know, the perpendicular axis theorem and the parallel axis theorem can be used for the calculation of the moment of inertia. So I have taken the two examples here. One, to calculate the moment of inertia for a square plate about different axis, okay, and the second, the moment of inertia of the rectangular plate. Okay, so let's derive first. I have taken a square plate. The mass of this square plate is m. It is a uniform square plate and the side of a square plate is a. And first I need to find out about the y-axis. I need to find out iy, as you can see here, right? I need to find out iy. Okay, so now think it. Can we use the integration? Yes, we can use it, right? And we know the moment of inertia of the rod. Can we break this square plate in form of the rods? Think it. Okay, we can, right? See, if I take a elemental rod somewhere here, right? Let's assume that the thickness of this rod is something dy, then the moment of inertia of this rod will be di, and the length of this rod is a. Let's assume that the mass of this rod is dm, so then it will be dm a square divided by 12, right? And now I can integrate and find out the total moment of inertia. So I will be integration of the di, and that will be integration of the dm a square divided by 12, right? Now a square divided by 12 is just a constant. I can take out from the integration. So I will be a square divided by 12 integration of the dm. And what is the integration of the dm for the complete plate? It will be the total mass of the plate. So that's why iy will be m a square divided by 12. So I have used the integration, and using the integration I have calculated it. Okay, think it. Can there be another way to calculate the moment of inertia? Can I shift the mass? Yes, we can shift it. Think it. If this is the elemental rod, instead of keeping this elemental rod at this place, if I shift it at this place, the moment of inertia of this elemental rod will not change, right? I am shifting this green color rod to here in the yellow color, because the parallel distance of the mass, perpendicular distance of the mass from the axis of rotation is not changing. So that's why the moment of inertia of the complete rod is not going to change, right? Yeah. Similarly, I can shift all of the elements at this place. So effectively, I can say that this square plate is equal to a rod, and rod will not have any dimension, just one dimension, the length. So the length of the rod is equal to the side of a square, that is a, and the mass is m. So I have shifted all the mass from this place to this place, all the masses, all the elemental masses. So now the mass has become total mass m, and the length is a, and we need to find out the moment of inertia about the center of this rod, and that is m a square divided by 12. So this is how I can use the shifting of mass and calculate the total moment of inertia, right? And now look here. Next I have taken, so first we have calculated about the y-axis, second about the horizontal axis, or I am calling it as the x-axis. I need to find out about this. Look here in this figure, about this. If I rotate this figure 90 degree, will this orientation, the second figure, will it become same as the first figure, right? So I can directly say that because ix and iy, the mass distribution about them is symmetric, so I can directly say that the ix is equal to iy for a square plate where x and y are the axis passing through the plane and the mid of these sides, and that will be ma square divided by 12. Or you can use the shifting of mass again for this case as well, right? Okay, let's look how we will use the shifting of mass. So instead of taking this complete square plate, if I take an elemental rod somewhere here and shift this elemental rod to any place, okay, so if I shift this elemental rod from this place to this place, moment of inertia will not change. And similarly, I can shift all of the elemental masses, right? So effectively it will become a rod of side, because this side again in this case is A. Look here, I have taken a square. If I take a rectangle, then it will be different. And the next is that case only that we are going to derive, right? So I need to find out about that. So again, that same, the moment of inertia of the rod about the center, that is ma square divided by 12, right? So you will get the same answer. I hope you understand this concept. The shifting of mass or integration and taking the element, there could be different ways, multiple ways to calculate the same problem, right? Now this is the square plate and I need to calculate about the z-axis. And see, look here again, I want to say that the z-axis is not the z-axis. It can be anything, right? So z-axis is perpendicular to the plane. Just keep in mind. So z-axis is this axis. I need to find out the moment of inertia about that. So look here, I have taken the two axes in the plane. Let's call them as x-axis and y-axis, right? And z-axis is perpendicular to the plane, right? And if you look in the top view, this will be the top view of this. This will be the top view of this square plate, right? So this is ix, iy. Now think it how to calculate. Can we use the perpendicular axis theorem? Yes, we can use the perpendicular axis theorem, right? Why? Because it is a planar surface. Z-axis is perpendicular to the plane and ix and iy are passing through the plane and they are also perpendicular to each other. So from the perpendicular axis theorem, so I can say from perpendicular axis theorem, iz is equal to ix plus iy, and for a square plate I know that ix is equal to iy is equal to ma square divided by 12. So it will become 2 times of ix only for the square plate. This is 2 times of ma square divided by 12, and we got the iz. Wow, that is ma square divided by 6. Look here, you need to keep in mind these formulas. You also need to understand how we can calculate. But if you are preparing for the competitive exam, so you will not have the sufficient time to derive these formulas again. So you need to keep in mind. And how you can keep in mind all these kind of information? By the logical understanding only, right? So you need to understand the method, and from there you will be able to keep in mind, okay, there was that case, we could apply the perpendicular axis theorem and then we can calculate, and the answer would be the ma square divided by 6. Okay, so this is how you will keep in mind. Okay, you are not going to mug up this. Okay, yeah. So now next, moment of inertia of a uniform rectangular plate. Of course I have not written down uniform, it is uniform. Okay, the mass of this plate, consider the mass of this plate is m, plate or sheet is m. Okay, and I need to find out iz. So here in this case I am directly calculating iz. Okay, so again we know that we cannot calculate by the integration. So what we will do, we will use the perpendicular axis theorem. So here this is the top view of this rectangular plate, and this is the horizontal axis, right? Okay, let me draw it again. Yeah, looks nice. And this is another. Great. So this is x-axis, this is y-axis. So if somehow I can calculate ix, iy, using the perpendicular axis theorem, I can calculate the iz, right? So now the method that we have used for the square plate, the same method we are going to use for this rectangular plate, right? Okay, so just think it. Can you give me the answer? Can you directly give me the answer? Just think it. What would be the answer? Will it be m l square plus b square divided by 12? Okay, just think it. Okay, so now let's derive it. So look here. Let's first find out the ix. So for x-axis, I can shift the mass parallel to x-axis. There will not be any change in the moment of inertia. So for the x-axis, I can assume this rectangular plate as a rod whose length is, let's consider this was b, so whose length is b, and then we are shifting the mass like this for the x-axis. Okay, so this will be a rod of length b, and a axis is passing through the center, and that is the x-axis. So ix would be m a square. So this ix would be mb square divided by 12 using the formula of the rod. And in case you don't know the formula, a moment of inertia of this rod, how it is m square divided by 12, we have derived it in the previous lectures. So go through the playlist, you will find the moment of inertia of the rod. Okay, you can understand there. Now we need to find out about the y-axis. So for the y-axis, again I can shift the mass parallel to the y, and there will not be any change. So if I shift these masses like this, at some point there will not be any change, right? So it would become a rod. Let me draw it again. It will become a rod. My drawings are not perfect, my writing is also not good, but you need to understand it. Okay, so this length is L, right? Mass is m, and iy would be from here, it would be m l square divided by 12. And now using the perpendicular axis theorem, we can say that iz, or the moment of inertia about the axis perpendicular to the surface, is equal to the ix plus iy, where these two axes are passing through the plane of the body and perpendicular to each other. So iz would be m b square divided by 12 plus m l square divided by 12, or we can say that iz is m l square plus b square divided by 12. Keep in mind, this will be the formula. You also need to understand the method behind it. Okay, so that's all for today. Thank you.